analytical chemistry, it is mostly impossible to measure concentrations or amounts of different chemical substances directly. You cannot count molecules, you do not see them. You cannot just weigh one component of alloy, leaving all others. So what we do, we usually measure some property of our solution or of our sample and then relate this number that we measured to concentration of compound or element of interest. Now, to do that, we need first calibrate our procedure, figure out how amount of our compound is related to amount. Most common and most convenient way is to measure proportional properties, which means you have a straight line. When you want to build a straight line, you want to measure several points, this, and more, and then make the best possible straight line coming through them. As you can see from this example, the real experimental line does not go through the points. There are some deviations. What we want to do is to make these deviations as small as it is possible. There is an assumption made by Carl Friedrich Gauss, same Gauss that we were talking about for a long time now, that all errors are distributed as Gaussian. Well, as all errors actually do. Then we can fit the curve by assuming that we want to make these deviations as small as it possible. But deviations can be negative or can be positive. So we cannot just add them. Positive and negative will make zero even, so total absolute value will be large. Of course, we can take absolute value of all deviations, but this will result in a difficult mathematics. To simplify the problem, we can make blank measurement. So measure our property at zero concentration, zero amount of our compound of interest. Again, this is not always possible. In this particular example, it wasn't. So instead, what we do least squares. We calculate the distance of our calculated value and our measured value. Square this. When we square any number, it becomes positive number. Then we calculate sum of these deviations over each measurement point. And the last thing, we require this sum to be as small as it possible. So square of all deviations should be as small as it is possible. Now, this mathematical problem again was solved in linear algebra by the same Carl Gauss. As a result, we have a straight line y equal kx plus b, where b is intercept and k is slope. Of course, our numbers k and b have some errors, and that's why we have uncertainty. This uncertainty is smallest in the center of measured data. It's slightly inconvenient because we want to have our uncertainty small when the numbers themselves are small. So it's a good idea to reduce uncertainty at low x by measuring multiple blank points and then have better statistics for these points and reduce uncertainty in this area. Now, I will not go over mathematics of this problem. You can look it in your textbook, but honestly, it's almost useless because we have software that can solve this least square problem for us with no challenges very easily, and then we'll leave mathematics to mathematicians. So let's look at an example. This example follows the example in Skoog's textbook. So we look at calibration data for chromatographic determination of isooctane and hydrocarbon mixture. Now, at this moment, I know nothing about this procedure. What I know the results. So I have mole percent of isooctane in this column and peak areas in this column. So peak area is linearly dependent on percent of isooctane. So first what I do, I enter all these numbers into Excel spreadsheet. Next, I use Excel functions. First function that calculate me slope of my straight line. Function is named slope, and arguments are our measurements and here are concentrations. I'm getting this result. Next, I'm calculating intercept. Again, the function is named intercept and arguments are exactly the same. So I highlight this area and then I highlight this area. So I have complete description of my function. Next very convenient parameter is square of correlation coefficient. It's easy to calculate again using the same parameters. Function is correl and you square it, so of course it's positive number. This number should be as close to 1 as it is possible. Actually, there is empirical agreement that this number should be larger than 0.995. If it's smaller, your calibration is of poor quality. In our case, we are good enough. Now, we can plot it on a graph, and you can see that experimental points visibly deviate from our straight line, still close enough. Again, this is the simplest way to do it. You can do the same using so-called array function, line est. You see the description of it in your textbook and in supplementary material on Blackboard. Alternatively, you can use data analysis tool pack. How to use it for this problem? Again, you have exactly the same Excel file. You're opening data analysis and now you select regression, plotting straight line through points. We name regression. So we select regression and such a window appears. So we select points that are in Y range. Then we select points that are in X range. We want to see our calculations to confidence level of 95, or we can put any other number here. And then we select place where output will be located. It can be on the same place or you can have it on separate new worksheet. Usually I prefer to have a graph plotted at the same time. Then I click OK. So here I'm having my result, r square, exactly the same number, 99.6. Now I have value of intercept and value of my slope. I have error of intercept and I have error of slope. I also have confidence interval for my intercept and for my slope. You see, that's quite a large interval because number of points is small. Now, from line fit plots, I'm getting this plot, which is essentially the same as we had before. It shows predicted points, straight line, and real measure points. So two approaches in Excel give you quickly, in seconds, exactly the same result, and you can skip very complex mathematics in your textbook. Leave it for your math statistics class. Now, what to do if I do not have linear function? You can linearize your nonlinear function to make straight line. What we do it by substitution of variable. For example, you have exponential function y equal to b multiplied by ekx. What we do is taking log function of two sides, natural log. So your new function y is natural log of y, and intercept will be natural log of b, again it's constant, and then you'll have kx. It's linear function, straight line, and you can process it as usual. Another common option is power function. You have y is b x k, where k is a parameter. What you do, you replace y with new function, which is log of y, and x, new x will be log of x. So your new function will be, you're simply taking log of all this expression, y log of b plus kx. Now it's a straight line again. Next, what if you have expression y is b k x square or x cube or x power something that you know, but it is not 1. You replace your x as x power a and you have new expression. For example, if you have a equals 3 and your equation is y equal b plus kx cube, you name new variable equal to x cube and you have linear function. If you have reciprocal a minus 1, so y equal b plus k divided by x. What you do, you say x is 1 over x, and your new expression is y equal b plus kx. So you have all linear functions, and you can process them in Excel exactly the way we did before.